Nikita makes Rust interactive, so if learning it is your directive, you won't need to fight to see what's inside to become a debugging detective.
Hi, I'm Nikita, and today I'm going to share with you a different approach to writing documentation and educating people about programming in Rust. So let's start by defining the problem. So what exactly is learnable programming? It is defined by Brett Victor in his essay of the same name as a set of design principles that helps programmers to understand and see how their programs execute. And some of the defining characteristics of this idea are seeing the state of a running program and giving the programmer tools to easily play with their code. And these things become especially valuable and important when they are applied to the problems of education and writing documentation because they can help to lower the entry barriers for people who are new to programming. And today I'm going to show you how we can apply these ideas to Rust and systems programming in particular. So let's see how it looks in action. Let's imagine you're someone new to asynchronous programming in Rust and you want to learn more about it. So you go to the Tokyo's website and you see that they have some really nice tutorials. But before you can start experimenting with asynchronous code, you need to follow a number of steps because the examples provided in these tutorials have some prerequisites. And first of all, of course, you need to set up a new Rust project and then add dependencies through cargo. Then you can take a look at the code provided in this example, and this code connects to a Redis-like server. It then sends a request to set a key hello to value world, and then it sends another request which gets the same key and verifies that it has the expected value. But before you can run this example, you need to make sure that a mini Redis server is actually running on your machine. So you also need to figure out how to install and run it. But why don't we try including all the necessary dependencies right there on the same page so that a user can immediately run this code and see the results? So this is how it might look. I go to the same example and I just click on the run button. So this code is compiled, and on the right side, I can see that a key hello has been successfully set to a value world. This gives the user an immediate context and response of what happens with their code, and the state of the mini Redis server can be also observed right there in the browser. But we can take this idea a little bit further and make this code example editable. So I can change the value of the key and run this code again, and I can see that the state has also changed. Or I can add a new key value pair like hey RustFest, run it again, and see that there is a new key now. This approach minimizes the required setup, so I can start experimenting and exploring the Tokyo API right away. And I believe that this is something that we should do to make Rust more accessible to more people. Well, of course, setting up a new project is also an important skill, but a first impression to show that this whole thing is not really that complicated is also important, I think. And well, it's not some kind of magic because we already can make it happen. We are able to run the Rust code in the browser by using WebAssembly, and the platform support is constantly expanded and improved in the compiler, so we can make it work quite easily. So when you click on the Run button, the code that you have in the editor is sent to the server where it is compiled by the Rust compiler, and a WebAssembly module is produced as a result. This model is then executed in your web browser, and you can see the output. This approach can be expanded way beyond just Tokyo or any other single library because we can use it to enhance documentation that is produced by RustDoc automatically. And all code examples can be made into this kind of interactive playgrounds, which you can execute in your web browser. And well, it already kind of works like that with the standard library documentation, because if you go, for example, to the page that documents vectors, you can just click on the Run button in any of the examples, and you will be directed to the Rust playground where you can see the output. And of course, you can also play with this code and change it. But what if we make it simpler by running examples in the browser on the same page and showing the output besides the code? This will make it easier for people to just immediately see the output without switching the context. But there's a problem if we go beyond the standard library. So the problem is, how do we deal with dependencies, and especially those dependencies which don't compile into WebAssembly yet? Well, the thing is, we don't really have access to dependencies on the Rust playground either, because Rust playground has a limited set of credits available to us since it's an isolated environment. And that's an expected thing, because the Rust playground executes your code on their server, and they just want to make sure that this code is not malicious, so they limit things like input and outputs, or loading the external dependencies. But on the other hand, this also makes it harder for us and makes it practically impossible to run examples from private code bases or even from public crates. And it makes it harder for us to mentor and educate people through examples. WebAssembly does not have this problem, because the sandboxed environment is not someone else's machine or server, but it's your own web browser, and this sandbox is secure by definition. But the main problem remains. Not all Rust code compiles down to WebAssembly yet. Well, some of it does, but even if it doesn't, well, you can argue that this is a good thing, because if you want to add this kind of interactivity to your project, it will also incentivize you to make your code more portable and make it compilable into to a new target. And there's a good chance that your code is already compatible with this interactive style of documentation, and that it already compiles to WebAssembly, because when you write tests for code that, for example, sends network requests, usually what you want to do is to mock it, meaning that your code won't really send real network requests, but instead it will pretend to do so. So you can test the behavior of your code in isolation from the external environment. And that is exactly the same thing that we want to do with our interactive documentation too, because we want to give a user the option to run their code independent of the external environment. And the main thing to look for here is the API conformance, because we want to make sure that mock functions that we call have the exact same interface as your real code. And well, you can do this manually by using feature flags, for example, or you can use one of the many Rust libraries for automatic mocking. But the main idea remains that you want to provide the same interface both in your real code and in the mocked version. And this idea of running the playground code in the browser can go a lot further, because we have lots of techniques for visualizing data. So, for example, on this slide, you can see some code from the documentation of an HTTP client library called request. It sends a GET request and outputs the response, but this example demonstrates only the only the abstract idea of sending an HTTP request, but how do we know how it actually works and what kind of request it actually sends? So in this case, we can output the HTTP requests, and it's really helpful to see what kind of request gets sent when you execute this code, because it can help you to learn more about HTTP. And more than that, it can also help you to debug problems, because with an interactive playground like that, you can just replace the code with your own code and observe the changes and observe its behavior. And the good news is that a lot of Rust libraries already do something like that with tracing and logging, but to use that, you also have to choose a logging library and enable it to just get the log output. And with WebAssembly enabled playgrounds, we just need to provide our own logging library that will redirect output from the logs to a user's browser. And the user's code can also be seen as data that we can visualize and inspect. And some of the components of the Rust compiler are already available as libraries, and there are even some more credits that can be used for parsing the Rust code. And almost all of them can be built into WebAssembly, so we can parse the code and extract the context information that we can use to show hints to our user even before they execute their code. It can make our examples even more clear, because these hints can be shown as a user types code, and they can provide context information almost like in the case of IDEs. And on this slide, you can see an example from the request documentation again, and it encodes parameters as HTTP form data. And as you look at this code in the editor, it can show some hints about what kind of result this or that function returns. And this is possible because the compiler provides us with meta information about the function names and the types that are used there, and all the kinds of expressions. And it's really straightforward to work with code as data, because all expressions are actually variants of one large enum. So you can use pattern matching to work with this enum just as you would normally do with Rust. And there's one more thing that we can do here, and that is highlighting the code execution flow. It can be compared to how you work with a debugger, which can go through a program step by step, and while it goes through the program in this fashion, it also can show the internal state of the program at this particular point in time. And we can do the same thing for our interactive playgrounds, because it can really help in understanding the cases like, for example, long iterator chains. And on this slide, you can see an example from the Rust standard library documentation, which shows how we can construct iterators in a functional style. And while this code kind of makes some intuitive sense, it's still hard to see what kind of output we will get when, for example, we call the filter function on the third line. But we can give a user a tool to go through this example line by line, while also showing what each function will do. And we can also combine this technique with the others we have discussed so far, because this time we can have access not only to the static context information that is provided by the compiler, but also to the dynamic state at the runtime. And we can display data like local variables or function call results. And as a user steps through the code, it becomes really easy to see how the state changes with each function call. With asynchronous code, this approach can really make a difference in understanding how it works. And if we treat each step as its own separate function call, we can do an interesting thing here. We can record the state at each step and store it, so we can move not only forward, but also backwards in time. And since we're talking mainly about things like short snippets of code and examples instead of like large code bases, it's possible to give a user a kind of a slider to go back and forth to really see the execution flow. Or they can just jump straight to a point in time that is interesting to them just by clicking on the slider. And again, this is not some sort of magic, because even if we don't have an immediate access to the WebAssembly execution engine in the browser, and we don't have a kind of fine-grained control over the execution, we can transform the user's code during the compilation step, and we can do that even without modifying and touching the Rust compiler. This transformation technique is actually pretty well known, and even the Rust compiler itself uses it for asynchronous code. So it works by basically breaking down each block into an individual function that represents a single execution step. This is known as continuation, and it means that we can continue the execution of a function from the point that we left it at. And Rust has an unstable feature called generators, and this feature is actually used for implementing the async await syntax. And well, it works almost exactly as you see it on this slide. So we have a struct that holds the internal state and things like local variables, and each block is transformed into a separate function. So when you want to execute this snippet, all you have to do is to call these functions one by one and record the state changes. So these functions can be called from the browser, and we are very flexible in choosing in what order we call them and what kind of state we record. And so far we have discussed some implementation details for these ideas, but overarchingly, how do we actually make it work and how to make it accessible to everyone? And there are several problems to solve here, and not all of them are technical. So first of all, the Rust compiler itself cannot be built into a WebAssembly module yet. So this requires us to have a compiler service that will build arbitrary Rust code into WebAssembly for everyone. So we already have something like that on the Rust playground, so it's not that big of a deal. And yeah, well, so I tried implementing these ideas in production for a systems programming course, and well, surprisingly, this infrastructure is not really hard to provide, and it's not expensive because a single CPU optimized virtual machine can easily handle hundreds of thousands of compilation requests per day. But still, we need to make sure that this infrastructure is easily available, and it should be possible to deploy it to deploy this compilation service locally and privately. But there is another problem that we have discussed briefly. If we start to include dependencies in our small code snippets, the compilation will take a large amount of time and resources, and the resulting WebAssembly module can have a huge size, easily taking up to several megabytes, making it harder to scale. And well, the obvious solution here is to compile these dependencies as separate WebAssembly modules instead, and then link the dependencies when we need them. But this problem is made worse by the fact that there is no dynamic linking standard for WebAssembly. So you're basically left with the only choice of statically compiling the dependencies. But technically, the linking is still possible, even though there is no standard way of doing it. It's possible to make two WebAssembly modules work together. So each module consists of functions that it exports, and that would be our Rust functions. And it also has functions that are declared as imported. And these imported functions are provided by the caller. And usually they are used for calling JavaScript functions from the Rust code And this is what makes it possible for Rust programs to interact, for example, with DOM and browser functions. So we can use this trick. When Rust module A calls some imported function, what we can do is to call an exported function from Rust module B. And this works, but this approach works, but there is another problem with it. Each module has its own separate memory, and this memory is not shared between the modules. And this means that if an imported Rust function tries to access its state when it's executed in the context of a different module, it will fail because this memory region does not contain the expected data. What we'll need to do is to basically copy memory from module A to module B before we can call an imported function. And the main disadvantage of this approach is, of course, that it's not standard, and currently it requires a manual implementation. Ideally, the Rust compiler should take care of this for us, but for now, to make it work in a general case, we'll need to find a way to automatically link Rust dependencies, which are compiled as WebAssembly modules. So now that we have covered all this, what is the conclusion? I think that it is well worth the effort to make our documentation interactive, because it will help us to bring more people into Rust. And part of the reason why JavaScript is so popular is that it's so easy to use it and access it. You don't need to do any sort of complicated setup. All you have to do is to open a console in your web browser, and you already can start writing code and experimenting with it. And with WebAssembly, we have a really good chance of bringing this simplicity into the Rust world. But we still have a long way ahead of us, because the WebAssembly ecosystem has not matured yet. But still, we can try our best in making this as easy as possible to add these sort of interactive elements to any project, because we already have tools like RustDoc, which can generate documentation out of the source code. What we will need to do is to improve RustDoc to also automatically generate playgrounds for our documentation, and we also need to have a toolkit to simplify building these interactive playgrounds. The good news is that we don't have to start from scratch. The most crucial part is actually compiling the code into WebAssembly, and the Rust compiler has got us covered there. We just need to build a tooling around it. So I have started a project that contains the Docker image for the compiler service and some front-end components. You can find the repository at the address you see on the slide. So if you're interested, you can join the development effort and help to make this a reality. And that's all for me, and thanks for your attention, and I'll be answering your questions in the chat room. Thank you.